So, you want to be an aerospace engineer. After all, conquering the skies and extending humanity's reach across the galactic wilderness is nothing short of extraordinary. Today, we're exploring everything you need to know about this stellar field, what to anticipate in the degree, the industry job opportunities, and real-life insights on what to expect for your career. Now let's discover what it means to be an aerospace engineer and give it to you straight. This is the reality of aerospace engineering. Starting it off with some context, aerospace engineering is a well-known and respected field concerned with every feature of aircraft and spacecraft design. These engineers utilize the same principles as mechanical engineers to design everything from Boeing 737s and hypersonic jets to the latest and greatest SpaceX rockets and James Webb Caliber telescopes, which is pretty awesome. But what do aerospace engineers actually do? Well, it's not a very simple answer. Like other engineering fields, there are a number of diverse systems that go into aerospace designs, meaning one aerospace engineer can have completely different daily tasks compared to the next one. So let's look at what a few of them do. Some specialize in propulsion methods, experimenting with various materials, fuel mixtures, and nozzle shapes to maximize the thrust of cutting-edge rocket engines. Others use planetary physics to strategize orbital roadmaps for satellites flung deep into the farthest reaches of space. And of course, some prefer the structural engineering that supports vehicles like the hypersonic rocket sled, ensuring that this sled traveling over 6,000 miles an hour doesn't simply collapse from the sheer forces of traveling over Mach 8. But before we get too far into the dazzling engineering feats, we've got to explore the curriculum that prepares these engineers to produce such amazing performances of technology. Oh, and make sure to stay to the end. We've gathered the 3 most important things that you absolutely need to know before starting an aerospace engineering degree. You're not going to want to miss this one. But more on that later. As a quick note before we get into the curriculum, each university does things a little differently, but the concepts discussed here are applicable to any aerospace engineering degree. Now, let's dig in. The aerospace curriculum starts you off with the Calculus series, which is nearly 2 years of derivatives, integrals, and related mathematical laws. Don't groan yet. The math courses just started. There's also linear algebra, differential equations, and probability and statistics courses to sharpen critical thinking and logical reasoning skills. Although years of math can get tedious when you just want to work on rocket engines, remember that it is the root of all of engineering and will be necessary later on. So make sure to pay attention and take good notes here. Anyways, these engineers also take computer science, CAD, and chemistry courses in their early degree stages. CAD is debatably the most useful of all of the foundation courses, as this technology drafts and simulates every single aerospace design before it is brought to life. Moving on, we have a smattering of physics courses that are jam-packed with useful aerospace material. You'll see kinematics, statics, dynamics, and electricity and magnetism courses. From fuel combustion to shuttle structures to the circuits riddled throughout the vessels, there isn't a single aerospace design that dodges the concepts taught in these courses. On a similar note, material science provides a baseline for how materials respond to stress, fatigue, and other forces over time. I don't know about you, but when I'm 30,000 feet in the air, I definitely hope the engineers who design the plane have a darn good understanding of these topics. Don't you? Anyways, we only have one more to cover before the illustrious aerospace-specific courses, and it is circuits, the bloodline that runs every single aerospace system. This course gets you into all types of methods and theories for solving DC and AC circuits, while learning about the properties of devices like capacitors, inductors, resistors, and some amplifiers. With this, you'll have the skills to understand the basics of oxygen control on spacewalks and data transmission from satellites to ground stations. It's more than likely that you won't be designing these electrical systems yourself. That work will be handed to an electrical engineer. But it is very important to have this base-level understanding of this circuitry, so you'll understand the electrical ins and outs of your system when discussing with the diverse group of engineers on your team. Awesome! Now that you're caught up, we can talk some real aerospace. But we've got to be honest, we've been hiding something from you. Throughout the video, you might have noticed that this degree doesn't only pertain to spacecraft. It also prepares students to work on aircraft and even ground vehicles as well. So let's spill the beans. Aerospace is actually composed of 2 distinct subfields, aeronautical and astronautical engineering. Aeronautical engineering deals with the engineering of aerodynamic machines in our own atmosphere, like planes, jets, helicopters, and even aerodynamic Formula One cars, bullet trains, and yes, rocket sleds. On the other hand, astronautical engineers cover the science and technology of spacecraft, working to create all types of vessels that perform inside and outside the Earth's atmosphere. So as we continue onto the aerospace-specific courses here, keep in mind that some apply much more to one concentration, and some the other. But don't worry, we'll have supplemental videos on each subfield for those who want to dig deeper into each one. Make sure to subscribe so you don't miss them. Now let's get back to the fun stuff. The first aerospace topics we'll touch on are the thermal courses. These dive deeper into the concepts of energy, control volumes, and cycle analysis, which are applied to realistic aerospace systems. You can find yourself looking at the efficiency of turbojets and turbofans, thermal protection in cabins, and combustion properties to maximize propulsion. Speaking of propulsion, this course is one of the most highly anticipated of all, and for good reason. Here you learn about the most popular propulsion systems and how they tick, or more literally, how they combust. In the aeronautics concentration, you'll find systems like the turboshaft, turboprop, turbofan, and turbojet. The turbojet is an intriguing system that takes air in from the front of the engine and herds it into a compressor, which is something like a series of household fans that squeeze air into an increasingly smaller area. This increases the pressure of the air, which then gets mixed with jet fuel, a type of super gasoline. Now you might be able to guess what comes next. This pressurized mixture is introduced to a flame that ignites and shoots very hot air and flames out of the back of the engine, providing thrust that propels the vehicle. Now, if that excites you, which, come on, how could it not? Make sure to see if your school has a space or rocket club. You could be getting hands-on engineering experience building a propulsion system of your own, which also will look simply fantastic on your resume. Now, getting back to the curriculum, some students are lucky enough to have access to wind tunnels so they can test the aerodynamics of their personally designed wings. How cool is that? These students learn that each airfoil, a cross-section of a wing, has a certain amount of lift and drag associated with it for a given angle of the airfoil. The name of the game in these aerodynamics courses is to apply various properties of fluid dynamics to design wings with optimal lift and drag for a given application. Now, on to the next course. The structures courses discuss the intricacies involved in building entire spacecraft or aircraft. This includes the general shape of the vessels and how they stand up to various vibrations, stress, strain, and displacements throughout their lifetimes. This is a great class to build up your finite element analysis skills. FEA is a numerical method used by software programs to divide larger structures into bite-sized pieces. Yep, another hard skill to slap on that resume. Once the structure is broken up, you're able to simulate how the pieces react to various loads and boundary conditions to ensure it won't fail under any circumstance. A very important skill. While a structural failure on an airliner would be an absolute catastrophe, an attitude failure for a satellite turns a marvel of technology into one really expensive brick. Attitude control is the orientation and orbital control of any spacecraft. And yes, it really is attitude control, not altitude. Each spacecraft has a very precise mission, like providing GPS services, collecting scientific data, or providing secure communications. If the orientation of this spacecraft were to flip and the antenna were to point out to space instead of down to Earth, it would render the craft completely useless. The attitude control courses teach you different methods to sense orientation and use software and actuators to bring it back to its correct position. The final upper division course we'll discuss is the Systems Engineering course, which basically teaches a high-level view of all the past classes we've discussed and how to successfully integrate them all together. Further, you'll discuss the importance of system-level requirements, stakeholder constraints, and project planning and tracking, but we'll save that for another video. Congratulations! You now have a solid understanding of the quirks, concepts, and concentrations of aerospace engineering. But now it's time for a lick of reality. We're here to give you the 3 most important things that you have to know before pursuing aerospace engineering. The first has to do with the job market you'll be entering after graduating. No, we're not here to tell you that this is a dying field or anything like that, but it is a subfield of mechanical engineering, meaning there aren't as many jobs available for you compared to if you went for a mechanical engineering degree. Searching mechanical engineer on Indeed results in just over 20,000 jobs in the US, while aerospace yields closer to 7,000. Not that this is the exact job ratio, but you get the picture. This smaller job field compels some that want to work in aerospace to go for mechanical, electrical, software, or other relevant degrees and then enter their aerospace industry from their respective backgrounds. The philosophy is that they'll still have the opportunity to enter the aerospace field, but will also have much more optionality if it proves to be too crowded. We do not recommend one path over the other, as this is a highly personal decision that is dependent on your goals and aspirations. But enough on that. Let's move on to the second important note about this field. You may or may not know that the majority of aerospace jobs in the US are defense-based, which can cause moral conflicts for some. There are a few non-defense related industries that you can enter, like commercial aircrafts, wind energy, and a few areas of the automobile and maritime fields, but you'll find that the majority of aerospace opportunities are in defense. Spacecraft commercialization is also a relevant and growing industry, but we wouldn't bet on a solid number of jobs just yet. So, before you enter the degree, we recommend having an outline of what jobs and fields you're aiming for so that you don't get trapped in a career path that doesn't align well with your passions or morals. Now, one thing that you absolutely do have to be passionate about when entering this field is wearing a lot of hats. No, not those hats. Engineering hats. Seeing as aerospace requires such diverse engineering systems applied to the relatively niche application of space or flight, engineers need to be technically proficient in a lot of areas to succeed in this field. As we alluded to earlier, you have to know enough electrical engineering to be able to properly communicate about the project at hand. You'll also need to know enough programming to inspect old code, write test scripts, and develop new control algorithms. Not to mention having a solid grasp on all of the aerospace-specific topics we went through earlier in the video. Now, you don't have to have wizard status in each of these fields, but aerospace engineers tend to have a deeper proficiency in their surrounding subsystems compared to other disciplines of engineering. This is why you'll see the mid to senior aerospace engineers typically gravitate towards the overarching systems engineering roles. They've been preparing for these positions for years. Now, with all of this in mind, would you become an aerospace engineer?